Welcome to the NITheCS Seminar series, also to the people that are online. And today we have the honor and the pleasure to have an honorary professor of the University of Pretoria, it's Stef Roux, and he studied electronic engineering at the University of Pretoria and has a PhD in electronic engineering. But then he also studied elementary particle physics at the University of Toronto, his PhD there. And some of you know him. I know him very well. I have collaborated with Stef for, I would say now, 15 years, so 15 years, something like this. And we had some very interesting moments. And it was interesting research, and I thank you again. I can invite you to this, but I think it's an interesting talk because it is giving us a new method how to deal with fermionic quantum field theories using Wigner functions. With these words, I give over to Stef, and can I have an applause for Stef?
Thank you very much. I'm very grateful for this opportunity to talk to you guys over here. So this is the picture more from the bosonic side. So this is just a 5 photon subtracted squeezed states, but I've changed the axis so it's not too squashed. But this is bosonic. What I'm going to talk about is fermionic. Now I should say I come more from optics, recently quantum optics, but I've had some exposure also with quantum field theory. So my interest in this is I've developed this functional approach to Wigner functions on phase space. And then I was interested, but what can you do for fermions? So of course, fermions, people have developed Wigner functions for fermions and so forth. But they haven't done it in a way that was traditionally developed for the bosons, which is based on the quadrature basis. So I was interested to see, can you maybe do this for a quadrature basis? And I had some success and made some interesting discoveries in the process, so I want to tell you all about that. So just to give you a bit of a background. So first I'm going to just briefly review the bosonic Wigner function and stuff. And you probably, or most of you may be familiar with just standard Wigner functions and things like that.
May I make a comment?
Sure.
We are not familiar with Wigner functions, most of us not, and also even not necessarily with quantum mechanics. So it is kind of, it would be very much appreciated if you could say something.
Okay, so I will try to make this as clear and as possible. But of course, I did not give a full lecture on it. But so here we just start with your ladder operators. So the ladder operators, just creation annihilation operators with which you create excitations, quantum excitations, right? Now it carries spin degrees of freedom, that's the S's and the R's, and it depends on your wave vectors and so on. So that's, in other words, all your spatial temporal degrees of freedom and your spin degrees of freedom are included. And they obey, in the bosonic case, a commutation relation. Now, this should contain the delta functions and so on, but I'm not going to bore you with all that detail. I'm going to write it in a simple notation. So this capital, this bold 1 represents an identity operator. So this is basically what you have. Now, the next thing that you do then is you convert this into quadrature operators. In the bosonic case, this is just the sums and differences of your two ladder operators, your creation and annihilation operators. They are now defined in such a way that they are Hermitian. And then you can now work out what their commutation relation is. And based on the commutation relation of the ladder operators, this is what you get. So you get the same identity, but with an I multiplied by now.
May I just for the clarity of the rest, in terms of harmonic oscillator, can I think of Q and P? What meaning do they have?
Yeah, okay, so you can go into like position and momentum. So if you think of a physical harmonic oscillator, the quadrature operators, you can think of it as position. The Q is like the position, P is like the momentum. And I know a lot of people talk about position and momentum. I stay away from that one, that terminology, because it is confusing. Why? Because the spatial temporal degrees of freedom is carried by the wave vectors. So the Q does not represent position in this case. P does not represent momentum in this case. It may be analogous to that. It's not the same thing. It's physically not the same thing, especially not in field theory. Okay. Are you happy? Okay. So the next thing then is you want to calculate the eigenstates and eigenvalues for this. So you have an eigenvalue equation. Now, I want to point out here, which is important, is your operator carries spin, degrees of freedom, and spatial temporal degrees of freedom. And obviously, that must be carried over to your eigenvalue. So it becomes an eigenvalue function. But your eigenstates don't carry explicit dependencies on these quantities. So that means that for every function, for every eigenvalue function, there is a unique eigenstate, which in turn means that the eigenvalue function parameterizes your eigenstates. Now, because there are so many functions, you can now think that the entire space of all possible functions is very, very vast. Of course, you can do the same thing for the P's. You get your eigenstates and your eigenvalue functions. So your P's and your Q's for your quadrature operators. And once you've done that, now you can define your Wigner functional. If it's just a Wigner function, then it means I've dropped all the other degrees of freedom. I just think of it as like a single mode state. And then you will define your Wigner function, which will be very much similar, but you won't have this funny diamond here. So what this diamond means is this. It means it's not two variables multiplied by each other. It's actually two functions. And you integrate over all the degrees of freedom and sum over all the degrees of freedom to define that. And that is the whole idea of a function null. All the degrees of freedom are sort of integrated out. They're not sitting there explicitly in the. Yes.
Would you allow me one more kind of for an explanatory question? So you said that the K vector is kind of representing the spatial temporal degrees of freedom. Can you elaborate on this? Can you say what we are dealing with?
So we're basically just in the Fourier domain. So in other words, I can think of this also as a function of x and t, x and y and z and t. But I'm working in the Fourier domain. So in field theory, your ladder operators are always functions of K. Well, but of course, I can also Fourier transform this. Yeah. So this just means I'm in the Fourier domain.
But would that correspond to the picture that my particles that I'm dealing with, let's say it's electrons, I mean here it's bosons.
Yes.
Let's say it's photons. No, I have photons, and there is some kind of field, and this field I can think of as maybe something that has waves, electromagnetic waves for the case of photons, and the K would kind of refer to the wave vector and the frequency or something.
Yeah, but it's a whole spectrum. So look, this is an operator, so it just excites and so on. But if I think in terms of, say for instance, I want to consider a arbitrary single photon state, like a clock state. I can define a ladder operator where, like this, I've got my operator, but then a spectral function. And then that spectral function, if I Fourier transform that would be such a way. And if, of course, what you would do the k is a three-dimensional vector, whereas my function is in space and time is really four-dimensional. So why do I get this difference in the number of dimensions? It's because they're on shelf. So in other words, they solve the equations of motion. That places a restriction that reduces the number of dimensions. So that's why I only get a three-dimensional space in terms of the k space, but I reproduce a field in space and time, four dimensions.
And as you mentioned, the Heidegger produces an excitation of that wave.
Yeah.
Now, for K2, it would be a plane wave, right? So a wave that has also
So in other words,
wave vector.
So in other words,
propagates.
that plane wave is the kernel of my Fourier transform. So when I build up this field in X and Y, I actually expand it in terms of these plane waves, but that is exactly Fourier integral. Okay, or in this transform if you want. Okay. Everybody on board?
Questions are allowed. Make it more lively.
Please, also what is X representing?
So this X is what I call an integration field variable. So this is a functional integral. So instead of integrating over just one variable, I'm integrating over functions. Okay, so this is why this is a functional integral. It's almost like, I don't know whether you know, ever heard of a path integral. Yeah, so it's sort of also the same family of things here. Yeah. So it's space for all functions to integrate. Good. Okay, so this is sort of the traditional way in which I think Wigner originally defined the Wigner function. Except not for the functional part, of course, but with the overlap of the two quadrature eigenstates, which are shifted in different directions. And you take the partial Fourier transform with respect to those shifts. And then you get the Wigner function. Okay? But there's also different ways that they came up with later on. For instance, you get something called the characteristic function. And what you can do is, if I want to calculate the Wigner function of this Roux, which is a quantum state, a density operator, I multiply this with a joint of a displacement operator. Here I give you the expression for the displacement operator. So then I trace that. And then I end up with a function, which is now a function of this displacement. So this theta is just represented in terms of these real valued fields. Okay, I'm still in the functional case here, but I mean, this is very similar to what you just did in a standard function case, in case where you have functions. So you see your displacement operator here is defined in terms of your ladder operators, your creation and annihilation operators, but I can write it also in terms of my quadrature operators, which would then be in terms of these real valued fields, which defines my characteristic function. So this is also a way to do it. This characteristic function, you then perform a symplectic Fourier transform to produce the Wigner function. What do I mean by symplectic? It's because you basically do a Fourier transform and an inverse Fourier transform simultaneously. And you get this relative minus sign between the two things. Okay. Now, this is in terms of the real valued fields in the language of functionals. You can also represent it in terms of the complex valued fields, still in the language of functions. Just replacing these things. And there now I've written it as an alpha. And alpha is just P plus IQ with a 1 over 2. So it's just a complex combination of my Q and P field variables. Okay. I can also do the P and Q distributions. I'm not going to talk much about them, so don't worry if they are. If you're not familiar. Yes.
So this characteristic function is there to kind of express the Wigner functional, or what is this character?
So the characteristic functional is like a generating function for the moments of all the moments of the Wigner function. But in a sense, you can say, because it is related by a Fourier transform, there's a one-to-one mapping between Wigner functionals and characteristic functionals. So it contains exactly the same information, but they often use that when they want to calculate moments, because you just take derivatives with respect to the variables, and that produces the moments of your Wigner. Does that answer your question?
Yeah, but I have one more.
Okay.
And if you say the characteristic functional is this trace of a row, what is row?
So Roux is an identity operator for my state.
So that is a representation of the state of the electromagnetic field.
Yeah.
Okay.
Yeah.
You have the bosons, electromagnetic field. And the D, what is the D?
So the D is my displacement operator.
What does that express?
Well, so this is the adjoint. Well, the displacement operator is the operator you want to apply to, for instance, the vacuum state to produce a coherent state. So on phase space, it performs a displacement. So you can, if you want to shift your state from one point in phase space to another point in phase space, you apply the displacement operator.
And why do you need, I mean, I understand that you need the state because, you know, the Wigner functional for me is a kind of alternative description of the state of the electron. Would you say that is correct? And I understand that you repeat the row, but I don't understand the D. For D dagger.
Yeah. So in other words, it's almost also like a Fourier transform. If you look at this this thing, if you just ignore the fact that those are actually operators, think of them as variables, then you can almost think of this, especially when you look at it like this, with the eyes. This very much look like the kernel of a Fourier transform. So this is basically what you're basically doing. It's like you're expanding your density operator, which you define on Hilbert space, in terms of phase space. So so in a certain sense, you can consider this, if I want to reproduce the density operator with my characteristic function. Obviously, you do the opposite thing now, and then you can almost consider that like an inverse Fourier transform, where your characteristic function is now your coefficient function for all the displacement operators that you need to add to reproduce your density operator. Okay, so after that,
I'm very happy. Yeah.
good. Everybody else happy? Okay. All right. So that was the bosonic story. Now we move to fermions. So how do you do the thing with fermions? Well, you can do the same. So I showed you the two methods of calculating Wigner functional. Now we want to do a fermionic Wigner functional, and it's going to live on a Grassmann phase space. I'm going to probably tell you what this Grassmann function is. But let me just briefly show you that the formalism looks very similar, but the catch is that your ladder operators now obey anti-commutation. So this thing means instead of the minus sign that you usually have between two terms, you now have a plus sign. So it's A dagger plus A dagger A gives you the idea. So that's your anti-commutation. You are familiar with this, right?
No.
So now,
I don't know what that is.
okay, no problem, no problem. So so my fermionic ladder operators will always be, from now on, always be operators satisfying an anti-commutation relation. Now, this method is now taking over from the bosonic formalism to the fermionic formalism, but there is a catch. Because these operators anti-commute, when you now try to represent it on a phase space, somehow those phase space variables must also anti-commute. And this is what these Grassmann variables are. Grassmann variables are variables that you can write down. The moment you want to interchange them, you have to write them once. Okay? So that is your Grassmann.
So that just comes from the Grassmann algebra.
That comes from the Grassmann algebra.
I just for the general audience that we have here. So what is the physical meaning of this anti-commutator? Can you say that?
That's a very good question. Well, for me, what it means is this thing is non-local. Because I can take an operator here, I can take an operator here, and depending on what order I have a change in the sign. So it's not like in the bosonic case, where when things commute, they really means that as they separate, they have no influence on each other. With the fermionic case, the moment I change the order, even if they are one apart, we change the sign. So for me, it means there must be something local going on. So,
and what does that have to do with fermions?
well, the fermions obey the statistics. I don't know what else to say about it.
Yeah, maybe you explain what fermions are. Sorry, I'm pitching it too low, but it might be that low.
So fermions, electrons and things like fermions obey Dirac Fermi statistics, which are these anti-commutation relations.
Is correct. That it means that now all fermions have antisymmetric wave functions. So in the moment where you would have two fermions with the same wave function, then the wave function of two fermions is zero. So that can never have fermions in the same state. That gives rise to the periodic system, not to the Pauli exclusion principle that we can in the periodic system. So that's why we have special statistics that they cannot be the same state. But bosons like to be the same state.
Yeah. So in other words, I wrote down there's one, of course, the ladder operators must anti-commute with themselves. So if I have A and A, I get 0. But that means A squared must be 0. And that is where this Pauli exclusion principle comes from. So I can't have two creation operators for exactly the same state. Yeah, okay. Yeah. So let me just mention, so this was the one-dimensional case. I discussed this in terms of the function also for normal dimensions. But the one-dimensional case was originally explained by K over cloud. So that's where that originally comes from. But now what about the other way in terms of the quadrature? That you don't seem to find. And the reason is the following. If I would do the analogous thing with the fermionic operators, where I define two operators, which is now my quadrature operators, as the sums and differences of these things, then I find something weird. First of all, if you remember, the quadrature operators did not commute with themselves. Now, of course, commute translates to anti-commute in the fermionic case. These two anti-commute with each other, but they do not commute with themselves, whereas the quadrature operators commuted with themselves. Right? You would expect them to commute with themselves, but of course, because if you're now going to use this thing and you substitute this in here and you work this out, you see, oh my goodness, that would be like it. So this is a bit opposite to what you would expect in this. And for this reason, the analogy that you would like with quadrature operators in the bosonic case, for the fermionic case, it doesn't quite work. So it's a bit of a mess. So instead of that, I'm going to now introduce to you a different way of defining these quadrature operators to overcome this and to get something that works the way it does in the boson. Okay. So, and these quadrature operators, you can see they look very similar But the catch is what is going on here. There is a spin transformation. Now I just have to say, the convention I'm using here is a summation convention. So when you see two of these indices repeat, it means I'm summing over them. So we're not going to write the summation marks all the time, but this means the summation. So in other words, remember this S or R is the spin index. This is effectively now a matrix. It has the following properties. If I take this matrix, the complex conjugate, or if I transpose the two indices, I get a minus sign. So it reproduces the same matrix, but with a minus. And the other property, if I take one of these and I multiply it with itself, it produces basically the identity matrix. Okay, this is a Kronecker delta. In the two-dimensional case, when you just have two spin indices, you can think of it in terms of the Pauli one. Okay, so in other words, it's my fermion ladder operators, everything the same that you would have as in the boson case, except for the spin transformation. So the spin transformation is only applied to one of the two ladder operators, not to the other one. So you get this relative spin transformation between the operators. Okay.
So if you say in the two-dimensional case, you get the sigma matrix, Pauli Y matrix. But what is the R? Is it not just the two-dimensional spin? We have a high-dimensional spin.
I mean, I say two-dimensional case just so that it could be general. I'm not making any restriction. Most of the time in fermions, you only have two spins. So yeah. But I'm not making a restriction in terms of that. Yeah.
Sorry, I still have one question regarding why do we use the sigma Y matrix specifically?
So the sigma Y matrix has these properties.
Oh.
And I want these properties. Good, all right. So, of course, there are now consequences. Things are not going to be identical to the way it is in the bosonic case. One of the consequences is it's not Hermitian. Remember I told you the bosonic quadrature operators are Hermitian. This is not Hermitian. If I take the Hermitian adjoint, I get something that looks different. You see there's now a minus sign there. And in fact, it turns out that the Hermitian adjoint of my Q gives me a spin transformed version of my P, and the Hermitian adjoint of my P gives me a spin transformed version of my Q. So they're sort of related in the crossover. Okay, so I really have four quadrature operators to work with, except that they are sort of pairwise related. So now I can go and I can work out all the anti-commutation relations. And as I want, I now see that when I anti-commute them with themselves, they give me 0. This is how I want it, because this is analogous to the bosonic case. And of course, because of this relationship, I'm also going to get zeros when Q is anti-commuted with the adjoint, the emission adjoint of the P, and vice versa. Then, the interesting thing is when I take a quadrature operator with its emission adjoint, it doesn't anti-commute. And if you look at this, you see, oh my goodness, it looks exactly the same as the original ladder operators. And that's a property of Boglie-Bott transformation. So in other words, they behave like Boglie-Bott. If I take those two pairs, they behave like Boglie-Bott. And then, of course, the thing that I'm really after is when I take Q and P, and I anti-commute them, or I take the daggers, I get I times dagger. This is what we also do in the bosonic case. So there's some interesting things here. Now, the interesting thing about the Boglie-Bott operator, or the benefit of the Boglie-Bott property, is that I can now use this to help me to calculate the eigenstates of these quadrature operators. Okay, so that's what we're going to do next, unless somebody wants to do this question. That's fine. So we go. So now when I do my Bogleov operators, I just generalize it a bit. So it's still the same thing where I have a relative spin transformation, but I'm going to multiply it now with complex numbers, arbitrary complex numbers U and V. These are not Grassmann numbers, they're just ordinary C numbers. And in this case, because of the anti-commutation relation, they must have the property that the modulus squares sum up to 1. In the bosonic case, the Bogleov operators in the bosonic case would have a relative minus sign here. But for the fermionic case, it becomes a plus. Okay. And now I'm interested in the eigenstates. Now, the reason why I say that the Bogleov operators make life a little bit easier to calculate the eigenstates is because in the bosonic case, I know that the eigenstates are displaced suites eigenstates. So I'm expecting the same here. So in other words, these states are squeezed vacuum and then a displacement. So I can write them like that. Now I've already shown you what the displacement operator looks like. So now I just need to tell you my squeezing operator looks like this, where the C is again just a complex number, but this R is now composed of either two creation operators, annihilation operators, or two creation operators with a relative spin transformation in between. Now, based on what Professor Conrad told us a little bit ago, why do we need this relative spin transformation? It's to get the antisymmetry. Because remember, if I have two, say for instance, two creation operators, the result would be 0. Right? That is what this anti-commutation relation tells us. So to avoid that, we have this spin transformation between the two. That introduces the antisymmetry. So you can remember the properties of this matrix. If I want to interchange the A dagger and A dagger, I will pick up a minus sign. But because of the properties of this matrix, when I transpose it, I also pick up a minus sign. Then those two minus signs cancel, and so I get something that is nonsense. So that's how I define these two R's. I'm going to introduce a simple notation. Remember, I had the open diamond already when I just integrate the product of these two things. Now I have a black diamond when there is also this epsilon contracting these things via this spin transformation. Okay, so sometimes you're going to see the black diamond, sometimes you're going to see the white diamonds. The only difference is the black diamond contains this relative epsilon. Right? Yes.
Can I ask now?
Yep, sure.
So concerning the meaning of the squeezing of it, okay?
Yeah.
So in the usual case, where I know it for bosons, where you don't have this epsilon, but just AS.
Right.
The squeezing means something like a state that is of minimal uncertainty in quadratures, but not symmetric. So it has maybe a greater uncertainty in the Q operator, the generalized position, sorry to mention this, and then the P. So we can have minimal uncertainty corresponds to a volume and phase space, and we can squeeze it, right? So I have a feeling for that in optics. So recursive quantum optics, where these states are non-classical states. They are very quantum mechanical because they have this property. What if I do now the spin transformation? What does that mean in terms of the fermions? You know, how can I?
You ask
let's think of
difficult,
the
you ask difficult.
Yeah, you present a different subject. So.
Look, let me just mention, in the bosonic case, so the minimum uncertainty area is a property that the original state must have prior to squeezing. The squeezing has nothing to do with minimum uncertainty. So if I have a vacuum state, of course, a vacuum state is already minimum uncertainty, and then squeezing, it's a unitary process, so it just retains the minimum uncertainty. Okay? If I give you a thermal state, it's not minimum uncertainty, and I squeeze it, it is still not minimum uncertainty. Well, it just stretch one direction and the other. Now, it's more abstract in the fermionic case. Okay? So you can imagine that if you think in terms of phase space, you will get something that is very similar. You will get that in one direction, you squeeze it, in the other direction, you extend it. But the role of this spin transformation is to make this at all possible. Without this thing, this whole thing would be zero. So that you wouldn't be able to write down a squeezing operator without this. Okay? So there is a theorem in fundamental particle physics, the spin statistics theorem, that tells you you always have spin half. You cannot have spin zero in the form. So I think that may have something to do with that, is the fact that you always have to have spin. Spin plays a key role in this whole process. So this is how I understand. But for me, it's still very abstract, and so I cannot necessarily come up with all sorts of deep explanations. Okay. Any other questions?
I have one more. Can you tell us what the Bogoliubov operator is good for? What does
So, in the bosonic case, of course, it's a nonlinear process. We often use that to diagonalize things and so on. In the fermionic case, you can do some similar things. If you've got some complicated Hamiltonians, sometimes these Bogoliubov transformations help you to define these things that you can diagonalize. Complicated Hamiltonians become some nonlinear.
And what does it mean that the squeezed displaced state is an eigenstate of the Bogoliubov operator? Does that tell me anything?
Well, this is to do with the squeezing, right? So that, in other words, it is related to the squeezing process. That's what you're looking for.
If I do a Bogoliubov transformation, it's like
okay. So maybe I can tell you on phase space what happens. So the transformation displaces the points on the phase space in a way that if I have a certain state, it will become a squeezed state. So the Bogoliubov transformations tells you how those points transform in the phase space. Anything else? Yeah.
Just the last relation, I thought there should be minus sign due to the property of step 7.
There should be a minus sign where?
In the last relation.
A minus sign here.
Yeah, because epsilon, the conjugate of epsilon is minus epsilon, right? The conjugate of epsilon.
so. Yes, can I say? So if you take the line above, R is equal to
So
this, and now you take the adjoint. What happens? What do you get?
Okay. So in other words, yeah, you flip these things, you get a complex conjugate and you get a transpose. But the complex conjugates and the transpose, if you do minus sign, should cancel. Okay. So now I have basically given you a bunch of operators that are defined either by the contraction of operators on operators, either with white diamonds or black diamonds, or sometimes a contraction of an operator on a Grassmann function. So that's what these alphas are. Okay. So this is now a Grassmann. So we have these complex field variables in the bosonic case. It's more or less the same thing, except it's a Grassmann function. Okay? So now, in other words, if I would take, I have two such functions and I change the order, I pick up a minus. So now, with all these operators, I can now define an algebra. So I can work out all the commutation. Why is it not the anti-commutation? Because that's why I call them Grassmann even. There are two things that anti-commute. When I have two things that anti-commute, combined, they commute. So now they are the commutation relations as opposed to anti-commutation. So I can work them all out, and I can see that when I commute them, sometimes if they both had Grassmann functions, I end up just with contractions of Grassmann functions. But sometimes, you know, I get operators. So for instance, this R, this one Grassmann function in there, I get an operator. What is interesting is this last one here. These are the two R's. When I commute them, they give me this anti-symmetrized number. Now what I can do is I can use the anti-commutation relation on this side. Then I will basically get the usual number operator plus a divergent constant. So this divergent constant, you can think of it like this integral of the delta at 0. I know people don't like infinities. Don't break your head about it. Just keep track of it. But why? It must cancel. It's going to float around all over the place. Whenever you calculate something that you should be able to measure and lab, these infinities must cancel. Okay? Anyway, so but now we can also consider the commutation relation of this anti-symmetrized number operator with all the other operators, and here I list them. The interesting thing maybe is if I look at the RR diagram S, they form the algebra for SU11. SU11 is an algebra that we associate with squeezing, so that's maybe not surprising because we needed the R's and so on to define the squeezing operator.
What's the S again? So this was S.
Yeah, this is this anti-symmetrized.
But how can you calculate with this omega in the back there? I mean, how do you write the commutation relations? Will it drop out or will it always be infinite?
No, this is not an operator. This is just
it's a number.
Yeah.
But it's infinite, right?
Yeah.
So is it in all these relations there? And all these commutation relations?
No. They, I mean, if I keep it like this, you can see that it works very much like a number operator. So it reproduces a thing like that. I mean, you can work it out. If you don't trust me.
No, I just want to know if I take SR, for example, right? The last commutator.
Yes. There's no omega.
There's no omega. No. Because this drops out because of the minus.
Yeah, it just works. I mean, you have to take the RR, which is IA, and you commute it with this thing, and you will see that it just reproduces the R or the R dagger. I mean, this omega plays an important role at different times. So you need to keep track of it. Okay. Everybody happy? So now I'm going to calculate these eigenstates. Now what we can do is under the Hermitian adjoint, these things are, you know, I can flip them over. So when I flip them over, it means that I'm going to have to calculate the Boglev operator with two displacements on either side. When I work this out, I get the original Boglev operator, and then I get an expression that contains those alphas. Those alphas are Grassmann numbers. Now here, this eigenvalue function must be a Grassmann function. So that turns out that this thing will become the eigenvalue function. Then I need to apply the squeezing operators. So it's only going to operate on this term. So I can work it out, and then I get this. Now see, there is a combination of parameters with the annihilation operator and another combination with respect to the creation operator. Now, eventually, when I now want to calculate the eigenstate, I'm going to have a vacuum state on the one side. Now, the vacuum state would remove the creation operator. No, sorry, it would remove the annihilation operator, but it wouldn't remove the creation operator. So that means this thing must become 0. This now gives me then a relationship between the complex parameters that I define in my Boglev operators and these squeezing parameters. Now here you only get the magnitude of the squeezing parameters. I can also now consider the other one. So this is the right eigenstates. I can also consider the left eigenstates. They will have different squeezing parameters because I'm not expecting them to be emission adjoints due to the fact that the operator is not emission adjoint or self-adjoint. So when I then calculate it, that means that I must now produce this a 0 on this side. And but now I'm going to get, I put little bars on the x's, and then you get the different relationships with this. However, it's the same operator, so that means the u's are the same. So I can then get a relationship between the squeezing parameters for the left and right eigenstates. The displacement operator has no effect because I can displace it all over the place. It's only the squeezing. So the squeezing parameters are related for the left and right eigenstates. Okay. If I want to calculate those for the emission adjoint operator, I just need to take the emission adjoint of everything for this and I get the result. So that is immediate. Okay. So now I have the eigenstates. So the next thing is now to look at the inner products. Yes.
Before we do that, if you go back and explain why we are so, and in quantum optics, for example, one can look at similar relations just for the annihilation relation, right? But you do it on a higher level. You do it for these Boglev operators that are already combinations of A, if I understand. Yeah. Right. So why would you do them?
So remember, the reason is I'm looking for quadrature. And I've discovered that the quadrature operators behave like Boglev operators. So first, I study Boglev operators. I mentioned that it's easier because I already know what I'm expecting as the eigenstates of the Boglev operators. This is eventually going to help us to come up with these quadrature operators. I mean, I basically sort of gave away the result in the beginning, and now I'm going to show you that I arrived at that result. But I have to go through the process of doing it with these Boglev operators. Okay, this is going to be very important because there's an interesting thing that pops out. And I want to show you that interesting thing. We're almost there.
Get a reward.
Yes, that's the idea. Okay, shall I go on? Okay, so now the inner products. So the inner products mean I want to now look at those operators, the vacuum states, and the idea is to change this, commute them, whatever you need to, until they are in normal order. Or at least in such a way that when I apply this vacuum state, it's going to simplify my expression. So now I can combine the two displacement operators relatively easily and write it in terms of one displacement operator. I'm just going to eventually produce this factor as well. But then I also have the two squeezing operators. Now the procedure that I'm going to follow to do this, I mean, I'm not going to show you this whole thing. It's an extremely tedious calculation, but at least I'm going to explain to you how this works. So you write this out as a product of exponentiated operators that contains all the possible operators that you can generate in the process of trying to commute all this stuff. And you write it in normal order, except, of course, this is inside an exponent, strictly speaking, not in normal order. However, when you apply this thing to a vacuum state, you know that S is going to give you 0, so
You have to explain normal order.
normal order. Because the normal order is simply you always have your annihilation operators on the right-hand side of the creation operators. The benefit of that is when you work on a vacuum state, when it first sees an annihilation operator, it gives you 0. So the only thing that survives is the identity. So that's why for something like this here, okay, here I would operate on this side. So it's going to give me the identity the moment I've got a vacuum state on this side. Okay, does it make sense? Anyway, so but now what I do is I introduce this auxiliary there. This is sort of a trick that people use to do this. So I just put in this t in the exponents. Here I'm going to introduce functions of the t because I have no idea what it's going to come out to. The idea is that when I put t equal to 1, I get back the original operator. So eventually, when I put t equal to 1, it must give me the result I'm looking for. Alternatively, if I put t equal to 0, everything just becomes the ID. So in this case, all these functions for t equal to 0 must be equal to 0. Okay. And here, because I have only those two complex parameters, and I have these parameter functions, these Grassmann parameter functions, I'm expecting everything on this side to depend on that. So these taus are defined as contractions of a tau, where the tau is just the difference between these two Grassmann parameter functions. So this is how it's everything defined. When I now take this, take this thing and I put the two vacuum states on either side, this is what I expect to find. So in other words, my general expression for my inner product will eventually have this form. So only these two functions are really important. And now we can see this omega is sitting there. This comes from this. When you commute it, it produces this omega. So it's going to sit there. This idea is the only thing that doesn't have an operator in the next one. That's it. So this is what eventually I need. This psi is what pops out when I combine the two displacement operators. Okay.
So is that 0 basically?
Is what 0?
If you have infinity in there and then in the exponent of the minus sign, you get 0.
No.
Why not?
You need to keep track of it. You might have to make sure it cancels. You need to keep track of it to make sure it cancels. Yeah, so no, don't put it to 0. Okay. You'll see what happens. And it's actually kind of interesting. Okay, so the whole process, I say it's a very long and tedious calculation. It took me a very long time. You take the derivative with respect to this t. So that produces lots and lots and lots and lots of things. Then you remove as many of those operators by operating with the adjoint on both sides of the equation on the right-hand side. So that will give me sort of the derivative and the operator and then exponentiated operators with opposite signs in the exponents on either side of this operator. So then I can use my commutation relations to simplify all those things. I get lots and lots and lots of terms. It's basically in the end, it's operator with coefficients of these h functions of t. And now I can separate that into all the different equations for all these different operators. So I get 8 differential equations for all these h functions. Then I can solve them and I get solutions for all my h functions. And now I put t equal to 0 and I have my results. The two that we are interested in are given by this, where there's these S's and C's are the cosines and sines of my squeezing parameters. And in some cases, I've defined this as a phase associated with my squeezing parameters. So I also have them. Now I can take my H and to H functions and substitute it in that expression that I had for my inner product. And this is my final general expression for these inner products. Yes. 5 minutes left.
It's unfair because I asked when this. I mean, for those that want to stay for, yeah.
I'm 12 pages of 26.
Maybe you have to come back in a second.
Okay, I'll try to go through this very quickly. So now the inner products, we can look at them that they are normalized when you put all the parameters equal. You can have the situation where this combination goes to 0. And then when you also have that this combination goes to 1, then that inner product, you will end up with a singularity. So you have to use a limit process. So it then behaves like a delta functional for Grassmann functions, which is an orthogonality condition. The opposite situation, where this goes to 1 and this goes to 0, gives me phase factors. And that makes these things look like mutually unbiased bases. But this is counterintuitive. Why? Because this orthogonality condition seems to show up between the left and right eigenstates of the same operator. And we are not expecting that because these Bogoliubov operators are not initial. And moreover, the mutually unbiased basis seems to show up in inner products between a left eigenstate and its emission adjoint. You do not expect an eigenstate and its emission adjoint to act like mutually unbiased bases. So what is going on here? Well, we may need to read it from the heat states. So that is what is happening here now. So Thomas, no more questions. Sorry. So what we do is we define something called the fermionic adjoint. It's the emission adjoint and the spin transformation. So that means that when I apply an adjoint, a fermionic adjoint to my ladder operator, it takes it to the emission adjoint of that ladder operator, but performs the spin transformation as well. Same thing for the other way around. Also, my Grassmann parameter functions, I get the complex conjugate together with a spin transformation. So it's the fermionic conjugate is different from the complex conjugate. The interesting thing is, now I'm going to represent my fermionic adjoint with this double back. The emission adjoint and the fermionic adjoint of the displacement operator is the same. So it doesn't matter whether I use fermionic adjoint or emission adjoint or displacement operator, it's the same. But it's not for the squeezing operator. Squeezing operator, the emission adjoint comes out to be something else. The fermionic adjoint reproduces the original squeezing operator. So that remains the same. Okay. Forgive me if I rush through this. I have really a lot that I want to tell you still. What we want to do now is we are looking for.
I have to go to a function. Yeah, yes.
Good. I'm looking for Bogoliubov operators that are fermionic self-adjoint. So in other words, I want to apply the fermionic adjoint on my Bogoliubov operator and get back the same thing. The implication is that the right eigenstate, take the Bogoliubov, the fermionic adjoint of my right eigenstate, it reproduces my left eigenstate. Now, it doesn't take much to realize that what must happen is that the two coefficients must have the same magnitude, which means I put the magnitudes of my squeezing parameters equal to pi over 4. So then sine of pi over 4 and cosine of pi over 4 gets me the same magnitude, namely 1 over square root of 2. So when I now replace this into my expressions for my Bogoliubov operators, I produce exactly the quadrature operators that I've shown you right at the beginning. Okay. At some point, we didn't talk about that, but there were some phase factors, and for these two cases, I just need to pick these two phase factors, 1 and -1, minus I. That is because these phase factors are not restricted by these restrictions. So now we find this interesting situation where my quadrature operators, I told you they're not Hermitian, so they're not Hermitian self-adjoint, but they are fermionic self-adjoint. So if I do the fermionic adjoint, I get that the same way. Furthermore, I can now write down all the eigenstates for these quadrature operators. And it's just an arbitrary squeeze, arbitrary displacement, but the squeezing parameter is always either pi over 4 or minus pi over 4. So for the quadrature, it's pi over 4. For the other one, the dual of the quadrature, it's minus pi over 4. For P, it's minus pi over 4, and for the dual of the P, it's pi over 4. So the interesting thing is now you see that the Q and the P, the ket of the Q and the bra of the P are Hermitian adjoints. So that's surprising. You don't have that in the bosonic case. Okay.
I make a suggestion because we are running out of time. I would suggest that we give a second exhibit, not now, but via next time or online.
Thomas, let me see how far I can get. Okay.
Yeah, no, but
please don't interrupt me. So my inner products I can quickly write down in terms of these taus. Remember, the taus are the differences in parameter functions. So here I get it in this form. You can see that when it is the self-overlap, I have to use it in terms of the limit cases. When it's a cross-overlap, I don't get the singularity, so I just get these results. Now, what I'm going to do is I'm going to replace the taus, which are in terms of these parameter functions, in terms of the eigenvalues for my quadratures in terms of Q's and P's. And that is given like this. So if I work with Q's, my alpha needs to be replaced by a Q complex conjugate with a spin transformation, or the P like this with the I. And so when I do that, the self-overlaps become like this in terms of the Q's. And now you can see, if I cannot discuss it in too detail, so I ask you to trust me, it gives you the Grassmann Dirac delta function. Okay, so now you can see the self-overlap gives you the Dirac delta function. So this is the orthogonality condition that you sort of expected to see. And in the cross-overlap case, you do the same substitutions. Okay, this is all the detail for you to work it out, and you get this thing. Now, all these terms transform like phase factors. So if I would do fermionic adjoints, all that happens is they change sign. And this is an indication that these two bases are mutually unbiased. And this is what you expect in the same thing analogous to the bosonic case. Okay, so this is a summary of this thing. I mean, what I now did was, there was Q terms and so on. I just absorbed them in the bases, so I cleaned up the expressions. So now, if you have ever seen the inner products for the eigenstates of quadrature operators in the bosonic case, you would recognize them as being very similar. The only interesting thing maybe is that you have this black diamond, which means there's this relative spin transformation in the inside. Important to remember that they are the deals related by a fermionic adjoint. If you do perform the Hermitian adjoint, you actually produce the opposite basis. Okay? So now I'm just going to quickly show you, I can do the completeness conditions. So that is just my basis resolve the identities. I can test them by take this, overlap it with two P's. It now gives me these exponential functions. So that means that when I integrate that, I can show it reproduces the Grassmann Dirac delta functional. It also tells me these exponentials are mutually orthogonal. It's basically a orthogonality condition. So in other words, I can go and I can define a Fourier transform, Fourier theory. So, which is important because the next thing now is to define the Wigner function. So I need to have this Fourier theory. So in other words, I can, if I have a functional of the one, this Fourier relationship will produce a function of the other one, etc. So, now maybe I should skip this. All that this means is my phase space is symplectic, which is surprising. The fermion case, you usually expect it to be orthogonal. Turns out it is symplectic, like the boson case, which is symplectic. Okay, this is quite interesting. And at last, we reproduce the Wigner function. So this is now, for fermions, it is in terms of your quadrature basis, it now looks like the original definition of the bosonic case. The only thing is, you have to remember, apart from it being functionals, is that you have this spin transformation between these things. Of course, you can write it in terms of the Q basis, in terms of the P basis. You can show that it is Hermitian self-adjoint, so you can do that, provided that, of course, your operator is Hermitian. So this is basically the goal that we wanted to achieve. The only thing that I'm going to briefly show you is the characteristic function. Again, symplectic Fourier transform, but you have the requirements for that. You can do the inverse thing to go back. You can have the Weil transform, so I can map the Wigner functional back to the operator, which means my mapping between phase space and Hilbert space is invertible. Very important. It leads to the fact that my trace is the integral over the Wigner functional, and if I want to normalize, it means that that thing must integrate to 1. Same thing that you have in the and the last thing is just the star product. So in other words, if I want to calculate the Wigner functional of the product of two operators, it is represented in a star product, and you can calculate it, and it comes out to be some functional integral of the Grassmann function. All right, I'm through this. How much time do I have to go?
7 minutes.
Okay. Anyway, I leave this there and leave time for questions. Hope there is still some. Yes.
Yeah, if you don't mind. I mean, I'm not sure if I remember, you mentioned something about being symplectic as opposed to
orthogonal.
Yes. But just ask what that means briefly.
So, okay. I don't know whether you remember your classical mechanics.
If you took classical mechanics with me, you would have known.
In classical mechanics, you can show that the phase space is symplectic. So it means that if I have a canonical transform that converts a Q and P to a different Q and P, then that canonical transform, written as a matrix here, obeys this relationship, where this matrix is reproduced when you, so you take the transpose of the canonical transform matrix, you multiply it on this thing, and it just reproduces. Right? This is sort of the standard indication of the symplectic process. It means that this is a symplectic matrix, it belongs to a symplectic group, etc. For the fermion case, usually it's orthogonal, so you don't have these things. You just do the matrix with its joint, and it will give you the idea. But in this case, you get this symplectic joint, which is surprising because it's a fermion. Yes.
In terms of many body theories, where do you see the application of this?
So if you can now use this to formulate the states that you would have, then maybe you can apply what the Hamiltonian is, what the area you can do. You can do some calculations based on that. So yeah, I don't know. I mean, it's a bit general, but this is what I think that you can do. I have actually worked out one case, which I have in my publication. It's sort of a generalized James Cummings outcome, which I treat like a two fermion species process. And then I show that this thing reproduces some generalized version of Roux oscillation in that case. So yeah.
Yeah, well, I mean, I understand that you have the quantum optics background.
Yeah.
But in terms of, I mean, condensed matter systems, I mean, the icing model looking for phase transitions, you know, that sort of things.
Yeah.
It's still open.
It's open. It's open. That's probably the best way to say. Yeah. Okay. Any other questions? Comments?
Yeah, so you had the sigma y in there, no? And it begs the question that if you would look at some equations of motion, and you would calculate everything in terms of quadrature,
Yes.
would it be relativistically invariant? So if you make a Lorentz boost for something that acts on the spin indices,
Yeah.
but you have the sigma y that is kind of specific, and
Yes.
why can it not be sigma z? So
Yeah, so it is
do
specific
you have
calculation.
some
Yeah. Look, I've started to look at that, but I haven't actually. I mean, what I do in the original definitions, you know, when I have these commutation relations, you can write them in relativistic form so that they are. No. Yeah. So here, this identity, you can define in a relativistic invariant way, so that you can transform these things, the commutation relation that you say, regardless of how you boost it, etc. So you can do that. But if I now think of this in terms of like field operators, where I combine this with, you know, plane waves and with spinners that must transform, etc. Although I don't think that makes a big deal, because your spinner, you define your Lorentz transformation to operate on the spinner, not on the indices. I mean, you can convert it into a transformation in the indices, but I think that should still work.
good, then let's thank the speaker again. Thank you much.
Okay, good.